Okay, let's get started. Whether you're watching this live or replay, welcome to this talk. Today we'll be discussing why microstructure can be a powerful driver of innovation, specifically in the field of rechargeable battery technology. I promise you today that after the hour, you'll have a better understanding of microstructure and how it can help solve some problems in research and quality control in this field. A quick introduction. Name is Pavel Sul. I'm the Chief Technology Officer here at MIPAR. Those of you that are new to MIPAR, we offer a software suite for building and running image analysis workflows, as well as hands-on consulting of image analysis projects. Here at MIPAR, we believe that material microstructure analysis can be a driver of innovation. Being able to see your material at this scale allows you to solve problems at this scale. I want to show you that your material microstructure can be part of your development process and not just a one-off project. So what exactly are we going to be talking about today? My goal is to give a relatively brief overview of rechargeable battery technology and the micro and macrostructural analysis. And I want to give everybody a better understanding how microstructural analysis can help drive battery innovation while reducing manufacturing costs. We'll first review the general structure of a rechargeable battery, then I'll have a brief note on advances in imaging technology. We'll then review the active materials in the battery cell and how to analyze their structure using imaging data. Lastly, I will talk about artificial intelligence, modeling and data mining, as well as simulation modeling. For the purposes of this webinar, we will use lithium-ion cylindrical design battery as an example. This is also known as a jelly roll design, though much of what I will be talking about is applicable to alternative chemistries and physical designs, such as the pouch design. So the layers of the cathode, positive material, anode, the negative material, and the separator membrane are rolled to create a cylinder. This is also known as a jelly roll design. I'm sure the original designer was a big fan of their grandmother's dessert, right? Um, the electrical current is then routed through the tabs to the positive and negative terminals, and then this entire structure is encased in a protective shell. Um, the alternative pouch design may have been also inspired by the dessert. I don't know, but it just resembles a layer cake, right? Think about it as a flat design instead of a cylindrical design. So before we jump into the microstructural analysis of these components, I want to quickly talk about imaging devices. After all, it's really hard to do microstructural analysis without capturing an image of the material. The devices I'll be talking about are scanning electron microscopes, focused ion beam, SEMs, and micro CT. In the past, using these devices used to be an expensive and time-consuming effort that was difficult to justify. Most teams will rarely do this type of analysis and usually outsource to an independent imaging facility. Thanks to advances in imaging technology, I like to say that powerful devices are becoming more affordable and affordable devices are becoming more powerful. For example, a floor model SEM is expensive to purchase and operate, but a tabletop SEM can offer much of the same core functionality at a fraction of the cost. Look, even if you prefer to outsource the imaging, you can still take advantage of some of these advances through cost savings or faster turnaround times. If your team has not shopped around in a while, I simply encourage you to take a look. One last note before we dive into the microstructure, keep in mind that these MIPAR solutions that I'll be demonstrating today are not limited to everything I'm just showing. So I just picked a few applications to highlight a broad range of microstructures in this field. So let's get back to the topic at hand. Look, it doesn't matter how you cut the physical structure of this metaphorical dessert, right? The electrochemical structure is the same. We have a lithium ion cathode, a graphite anode, separated by a separator membrane. Let's first focus on the precursor material. Specifically the graphite used in the anode. The final packing morphology of the battery anode is dependent on the size and shape of the graphite, right? And as well as the presence of any particle, any contaminants. Right, so why should you care about the packing morphology of the graphite? Simply put, this packing density drives the interaction between the anode and the electrolyte. This in turn has an impact on the energy density, life cycle, and safety of the battery. As you can see, flake graphite mixed in with spherical graphite will result in inefficient packing. Same goes for variable graphite size. Consequently, inefficient packing will result in reduced performance. Let's jump into MIPAR for a quick look at modern detection and analysis has to offer. I'm going to open up the image processor, and I'm going to load in a sample image by dragging and dropping into the interface. From here, I can load in the recipe by simply dragging the recipe into the interface, and MIPAR does the rest for me. What you just saw is the analysis being done in real time. This is being done on a laptop, not on a computer in the cloud. This helps make this technology much more accessible, as well as secure. So what we see here is our particles that are being detected in red, as well as a summary report of what the detection is. Right, so from here, what I can do is I click the green play button and the feature measurements. And MIPAR pulls up a color by measure report of the aspect ratio. I can do the same thing for the caliper diameter. And from here, I can simply print the report, click generate report. And MIPAR takes all this awesome information and packages up for me into a Word document that I can add comments to, a signature, and send out to whoever needs to take a look at this data. Now, those of you that are working with particles understand that statistical significance is really important here, meaning that you really want to be able to measure enough particles to make any conclusions on the morphology and the size of the particles. So for this, MIPAR has the awesome batch processor, where what we can do is load in our recipe by dragging and dropping it into our interface here. I'm going to use a synthesized data set for this case. And basically, the data set just ensures that I have measuring enough particles. So let's go ahead and click process. What we see here is that I'm processing about 20 fields of views in under 15 seconds. We're going to let this complete. We'll view the results. We can now take a look at the detection. So everything here that's in red has been detected. I can change this to outline view to see exactly what's being selected. Go back to overlay. I can then generate my measurement by selecting features, selecting the caliper diameter, the aspect ratio, and then selecting view measurements. From here, I have a measurement table. I can select the cell, and then it plots the distribution of my aspect ratio. I can do the same thing for the caliper diameter. A lot of powerful data can be derived from curve fitting, so MIPAR has that built right into the interface. You can select the log normal distribution, my curve fit, and let's again print out my report. I can trust that this data is accurate. I have my distribution, my statistics, and this can be sent out. MIPAR automatically saves my session. So let's say I want to go back and review my session at a later date because I want to see what the report, what was detected to generate the report. It's very easy to do that with MIPAR. I can simply select load session, select my session, and MIPAR will load in all the original images as well as the detection for me. If I want to make any changes in my detection, I have all the tools here in front of me. Simply zoom into the particles I want to adjust. Let's say I'm not interested in measuring these particles for whatever reason. I can select them to remove them, save, zoom back out, and I can regenerate my measurements. And just like that, I have a quantified, repeatable, traceable, and minimum error method to do graphite qualification. Both material suppliers and manufacturers can use this method to qualify their products for sale and downstream manufacturing. Look, when micrograph quantification is this easy, it facilitates further experimentation, like studying particle satellites or understanding the synthesized versus deformed spherical graphite packing density. So let's jump into our next layer here. And unfortunately, it's often overlooked. I'm talking about the separator membrane. Um, specifically, we want to understand the separator membrane pore size. This is a critical metric for quantifying how easily the cathode and the anode components interact. In some designs, the separator material can act as a final failsafe, as we see here on the left. In extreme thermal conditions, the separator material can be designed to reduce its pore size and isolate the cathode from the anode. On the other hand, under extreme conditions, a failed separator, like what we see here on the right, will result in uncontrolled interaction. This will in turn can result in thermal runaway. So why should you care about separator performance? Simply put, a well-designed membrane can ensure reliable performance and help meet safety standards. Let's jump right into MIPAR. I can load in my membrane, again by dragging and dropping it into the interface. Take the image file, drag it in here. Let's clear our recipe. I can do the same thing with my recipe file. Okay. And what we see here is my detection in red. For my detailed report, I can simply click the green play button. MIPAR generates my color by measure figure, my distribution, and just like before, I can output this into a Word document. And just like with the graphite analysis, what I can do is run this in batch process if I want to analyze multiple fields of view. This is a powerful way to qualify your material for further manufacturing and experimentation. Once again, when micrograph analysis is this easy, we can start to think of some pretty cool experiments we can run. For example, studying the pore size before and after the separator was cycled through extreme thermal conditions, or better understanding a pore morphology of different membrane materials. Okay, let's move on to our next layer. Specifically, we want to understand the interaction between the phases in the cathode. These interactions drive the battery cell performance and can help inform simulation models. Let's take a look at MIPAR. Looking at a sample image is always worth 1,000 words. So this image was captured using a new technique outlined in a recent publication in the Journal of Electrochemical Society, titled Kintsugi Imaging of Battery Electrodes, Distinguishing Pores from the Cathode Binder Domain using PT Deposition. This method allows for reliably capturing the contrast of all phases in the cathode. This is an involved technique using a PIPSEP device. So I'm not going to pretend like this can be done on a daily basis. Nevertheless, analysis such as this can provide volumes of data on the cathode composition throughout its life cycle. To describe this microstructure a little bit, what we see is the active particles in the light gray color, the carbon binder is in near black phase, and the porosity is in white. This imaging technique generates two layers of information: SEM through lens detector image and SEM concentric backscattered image. And I can pull up both of these separately. And what you can see is the through lens detector image is much more noisy than our concentric backscattered image. But using MIPAR, we can actually stack these two images together as colors. Now, this may result in some funny coloring, but fundamentally results in a very powerful piece of data. Thanks to deep learning, it makes use of the noisy layer provided by the SEM TLD image to actually make the detection and segmentation much easier. So let's go ahead and apply a recipe. Again, I'm simply going to drag and drop the recipe into MIPAR. This is applying a deep learning model in real time. Again, this is being ran on my laptop. So what you see here is an accurate detection of all three phases, at least the ones that we're interested in. My binder is in the red, my pores are in green, and the active particles are in blue. So the benefit of using MIPAR in this application, in addition to the very powerful detection here, right, is that it's trivial to set up routines to help answer some really cool questions. So for example, I want to know how much of my surface area of my active particles is interacting with my binder, right? So let's dive into MIPAR, set this up. I'm going to take my active particles, I'm going to dilate them a couple of points. I'm going to set this as a companion image. I'm going to recall my binder image. Again, dilate this a point. I'm now going to do an intersection between the 2 points, or 2 pieces of data. And I'm going to thin this layer. Awesome. I can set this as a layer now. And let's go ahead and assign my perimeter measurement. Let's just limit this to, there we go. Okay, and we can take a look at our summary. The cool thing is that just with those few steps, what I can see is that about 50% of my binder is interacting with the active particles, right? Because my perimeter here is about 516. My total perimeter of the binder is about 976. It's pretty neat that was set up in a matter of seconds. So a lot of times when working with FibSem data sets, the goal is to usually to generate a 3D volume. MIPAR batch processor allows you to do data alignment and creating a three-dimensional reconstruction. If there's interest, we can actually do a demonstration of our 3D toolbox in another webinar. Look, once again, when micrograph analysis is this easy and it's this user-friendly, you can start to think of some pretty cool questions you can ask over cathode composition, right? Like, for example, how does the internal porosity of our active material change through the life cycle of the battery? As well as, are there alternative electrochemistries that maintain surface interaction throughout this life cycle, right? That's talking about a little bit of component degradation. So the last application that I want to talk about today is going to be a CT application. I'm just going to go ahead and just load the image in here. The benefit of using micro-CT to scan your final battery or your final product is that it's non-destructive, right? So even though you can do electrical testing of the complete component, and it provides a wealth of information about the performance of that component, electrical testing does not provide the failure mechanism in case that component fails, or in case that there is a contaminant in the final build. Very rarely will simply electrical testing highlight that. Let's jump into the presentation here. Two highlighted applications in the recent IEEE publication are active layer thickness and collector tampers. Once again, thanks to advancements in micro-CT imaging, it's become much faster and easier to collect a serial section scan over final cell without the need to destroy the sample. Active layer thickness is a fast and easy way to identify layer thinning, which can result in component hotspots. The second application identifies the collector tampers, which in extreme conditions can puncture are multiple layers, resulting in a local electrochemical short circuit. Problem is that these defects do not manifest themselves as critical failures until the battery is damaged or degrades over time. They also do not show up during electrical testing. All right, let's get back to MIPAR and take a look at the solution. So what we see here is a cross section of our jelly roll, right? Let's go ahead and load our recipe here. What we see is that this is a supervised workflow where MIPAR will prompt the user to identify a potentially problematic region of interest. You can do that simply by doing that. And MIPAR does the rest for us. All right, so it finds this region of interest and then measures it. So the thing that we want to take a look at here is the maximum thickness of that burr relative to the layer thickness. And what we can see is that that burr is thicker than our layer thickness. And this is a problem, right? Because we can see how during component degradation, those layers can be pushed through the burr or vice versa, puncturing the layers. At the same time, the battery can be damaged, and that burr will be a mechanism of failure by puncturing the layers. So that's a pretty cool report that you can simply output by selecting print report. MIPAR shows you exactly what was detected and what's being measured. You can add the comments and add your signature. The other cool thing is that you can generate a local measurement of the layer thickness. This will measure the layer at every single point along the layer thickness, and it becomes very easy to highlight potential layer thinning. Now, layer thinning is important because it can result in local hotspots, which lead to um, accelerated degradation of the component as a whole. So, again, when macrostructural analysis is this easy, there's a little reason not to explore it as an option. Okay, so now that we have reviewed some real-world applications, I want to jump in and actually talk about a little bit more about exactly how MIPAR can help you innovate. Right. So the power of MIPAR is achieved through both the software suite and our applications team. Our software product enables fast solution development. Through our innovative implementation of deep learning technologies and our user-friendly interface that facilitates creative problem solving, simply put, we're able to deliver solutions that are accurate and repeatable faster than anybody else. Our application specialists hold a PhD in their respective field and bring a ton of experience and a ton of information to your project. Right. So what does all this mean to you in practice? Let's say that I am a lithium-ion battery researcher, and over the weekend I'm visiting my grandmother, and she's making my favorite dessert, a jelly roll, of course, right? And I have a brilliant idea and a hypothesis that I want to test. Now, this is my first project of this sort, and I'm not really sure how to image my sample or how to set up MIPAR to detect and measure what I'm looking for. Well, Monday morning I can come in, I can call in my MIPAR application specialist, and we have a quick call to talk through what I want to do. The application specialist can give me advice on how to prepare and image my sample. After the call is over, I send my sample out to be imaged, and realistically, by the end of the day, I have my image set. I can share the image set with my MIPAR application specialist, and they'll put together a working solution for me in as little as 12 hours. I am back the next day with a working solution that I can run to generate statistically significant data that I can trust. So in summary, by the end of the day on Tuesday, I'm able to draw my conclusion and make production decisions, right? That's basically a 2-day innovation cycle. So if I'm a more hands-on learner, my MIPAR application specialist can schedule a training session where they'll show me exactly how they built the solution. That way, when I have a problem that's similar in the future, I actually don't have to rely on them anymore. I can do it myself. And the awesome thing is that most of MIPAR solutions are robust. So when you're working on a similar project 2, 3, 4 months from now, you can actually use the same recipes you did before with some minor adjustments, which oftentimes just take seconds, like what we saw with the cathode composite analysis. Right. So let's say this project was a success, and I'm interested in deploying this analysis solution to a quality control environment. So I'm going to, it's fairly easy with MIPAR using our MIPAR Express product to deploy this to a quality control materials lab, and the entire protocol can be shared using a 4-megabyte file. Those of you that outsource your microstructural analysis and you're being quoted 4, 5, 6-day or week-long turnaround times, I'd encourage you to explore bringing this analysis in-house, or at least ask your outsourcing team if they have tried MIPAR. We've been able to help teams shave weeks off of their innovation cycle. When our customers implement MIPAR, they're probably solving toolsets expands. Imaging and microstructure analysis is no longer a one-off project they do. The material microstructure becomes a valuable data point to inform decision making. And as I said before, when you can see your material at this scale, it allows you to solve problems at this scale. In the fast evolving field of battery technology, a fast innovation cycle is the difference between innovating and just keeping up. So the next thing I want to talk a little bit about is AI modeling and simulation. And how microstructural analysis ties into all of this. Much like imaging technology, artificial intelligence has become much more accessible and powerful in recent years. I hope my demonstration of MIPAR's detection and measurement engine has demonstrated advancements in deep learning detection modeling. Some of those models can be developed in as little as, having 4 to 10 images annotated, which is a stark difference from the hundreds, if not thousands, that we had to do in the past. So this is not the only application that benefits from advancements in artificial intelligence. More and more, AI models are being used for predictive studies in manufacturing and research and development. Let's use our example of our spherical graphite. In this case, I'm a manufacturer of spherical graphite, and I'm collecting data on my manufacturing parameters. If I'm using MIPAR, I can start collecting data on the microstructural properties and use an AI model to tie my manufacturing parameters to my microstructural properties. Right? This model can then be used to predict my microstructural properties from my manufacturing parameters, or if ran backwards, I can type in what microstructural parameters I want, and the model will return the manufacturing settings I need to reach that the microstructure. Now engineers can then go in and tweak those manufacturing parameters to optimize to reduce waste or minimize or maximize cost savings. So the awesome thing about MIPAR is that it generates a ton of data. For example, if a micrograph image is fed into an AI training model, it's used as a single data point. If I take that same image and I process it using MIPAR, we can generate over 20 measurements per particle. So let's say there's 500 particles per image. That's 10,000 data points per image. Look, there are a few things that AI likes more than more data points. After collecting all this data, another cool AI modeling application is something that's called data mining or knowledge discovery. These models are trained to offer answer to questions that you've not even thought of yet, which is awesome because you don't have to think about the experiment at all. The model actually gives you data you can use about your own production process. So as a cool and easy to understand example of how powerful and accessible AI model have become, I wanted to share DALL-E, which is a engine that you can type in a prompt and it will actually create an image for you. So you can this is accessible using the website Crayon. But basically speaking, you can type in a prompt. In this case, I typed in painted battery, and it created a novel image that's never been seen before from scratch, right? Which is pretty amazing. And this is powered by deep learning technology. And if you are curious about more existential questions, you end up with something like, asking this thing to create a self-portrait, and this is what you get. which is, a pretty cool demonstration of how far this technology has come. This used to have to run on supercomputers, but now all you have to do is just plug this into a website and generate an image. To the extent that this actually won an art contest in Denver this year, which is pretty cool. Lastly, I want to have a quick note about simulation software, more physics simulation software, right? Those of you that have experience in that with those software packages, you know that starting conditions are critical when setting up a simulation. A good understanding of the material microstructure can provide the real-world structural conditions. For example, doing a physics simulation of the life cycle of the battery anode under varying conditions can offer insights into the physical and electrical properties of that component at all stages of the component degradation. The great news is that there are several teams that are doing awesome work in this space. A quick Google search will bring up some of the most popular software suites. Okay, so the question now is, how do you get started with MIPAR? I encourage you to give us a call. Right? If you have a project in mind, just email us or give us a call. We include a free solution and training with your professional license. And our proven onboarding process will get you up and running in a matter of days instead of weeks. I want to put this up here for a moment. These are some of my references that in my research to put together this presentation. And then some summary and closing thoughts. Do not forego microstructure analysis because it took a while in the past. They may no longer be the case. Thanks to advancements in imaging and analysis technologies. These days, MIPAR is used to qualify materials in both research and development and quality control projects. Keep in mind, microstructure can be used to inform manufacturing and product development decisions through direct material qualification, artificial intelligence models, or physics simulation software. Lastly, the replay links for this webinar will be shared via email. Feel free to share it to colleagues that maybe find this interesting. I had an awesome time putting this together, and by attending, you have shown great initiative to keep learning. So have a wonderful day and keep innovating.